I would like to look at section 2 of chapter 4 in the Practice of Statistics 5th edition, discussing experiments, and this will be fast and furious, looking at a bunch of terms and definitions and ideas, and then we can go through and talk about them in more detail after we understand a framework of what we're looking at. Here are the objectives for the units. As with the whole presentation, if you need to stop and read all this, just pause the video. I'm not going to go through all of those. First of all, the distinction between an observational study and an experiment cannot be overstated. It's huge. You must recognize the difference. An observational study will attempt to observe individuals, measure things, see what it can find out by looking and not influencing the responses. An experiment, on the other hand, will seek to deliberately impose a treatment on the individuals in order to see how they respond. In an experiment, you impose a treatment. In an observational study, you do not impose a treatment, you simply observe. The reason that we want to perform an experiment is to discuss cause and effect. The only way to demonstrate cause and effect is with an experiment of convincing data. Observational studies show the effect of an explanatory variable on a response variable. And sometimes they fail because there's a lot of variables that get all tangled up and it's hard to tease them out. So for example, a study might show that patients that go to the doctor regularly have better health care. But what's hard to pull out is the fact that patients that go to the doctor more often also probably have more money, and having more money is strongly correlated with having quality food and quality education, and those things are connected to having better health. So is it going to the doctor? Maybe, but there's a lot of stuff tangled in there, and you can't just pull one thing out over the other and say this is what the cause is. A well-designed experiment, on the other hand, will take steps to prevent the confounding issues and allow you to tease out exactly what the causes were or how much effect each explanatory variable had. An experiment is a statistical study in which we actually do something. We give a treatment to people or animals or objects, whatever they are. Those things that we give the treatment to are called experimental units. If experimental units are people, we will frequently call them subjects. The condition we apply is called the treatment. The thing we apply it to is the experimental unit. And if the experimental unit is a person, we will likely call it the subject. Many experiments might be set up like this. We have experimental units that we give a treatment to, and we measure their response. In a lab, the simple design may work just fine. Out in the field, there may be more variable conditions, and it becomes a little more complicated. But if you don't have a well-designed experiment, you end up with worthless results. So it's imperative that the design of the experiment is quality so that we don't have tainted or flawed results. Comparison is critical to the design of an experiment. But comparison alone isn't enough. If treatments are given to groups that are very different, we end up with bias. Bias is a systematic favoring of a certain outcome. We can avoid bias with random assignments. Sometimes random assignments will be called random allocation of treatments. This is a little bit different than what we did in the last section, where we did random selection. Previously, we were doing random selection. At this stage, I've already selected my experimental units or my subjects, and now I will randomize who gets which treatment. That's the random assignment. That random assignment will involve some sort of chance process. Flipping a coin, rolling a die, using a random number generator, something chance, rather than I picked it or eeny, meeny, miny, mo. We've got a few basic principles of experimental design. Sometimes you'll see 3 or 4, but here are things that need to be included. We need to have comparison. We need to be able to compare the results from 2 or more treatments. We need to have random assignment. We need to have chance to assign the experimental units to the treatments. The reason we need this is because by using randomization, we will likely end up with 2 groups that are relatively similar in a variety of characteristics, so that essentially we have 2 groups that are the same, and one of which will get one kind of treatment and one of which will get another kind of treatment. We need to control variables that might affect the response in such a way that we've kept the environment the same for all groups. We want to keep variables in check so that the only difference is the treatment that I'm imposing. And finally, we want to have replication. We want to have enough experimental units so that any differences in the effects of the treatment can be distinguished from just luck of the draw. So for example, if I only do it on 10 people, we'll say flip a coin. If I flip a coin 10 times, it's not terribly unusual to get only 2 or 3 heads. But if I flip a coin 100 times, only getting, say, 20 or 30 heads is a lot less likely. That's because of replication, because I've got enough experimental units so that I don't think it's just dumb luck or pure chance that resulted in these differences. In a completely randomized design, the treatments are assigned to all the experimental units completely by chance. Sometimes that includes a control group. The control group might receive an inactive treatment or a baseline treatment or a placebo. But I start with my experimental units. I randomly split them into 2 groups. Perhaps I flip a coin and the heads go one way and the tails go the other. One group gets one treatment, another group gets another treatment. And then I compare the results. This is called a completely randomized design. The logic of a randomized comparative experiment depends on our ability to treat all the subjects the same way in every way, except for the actual treatment being compared. Good experiments, therefore, require careful attention to details to ensure that all subjects really are being treated identically. We've also talked about a placebo effect and a double-blind experiment. A placebo effect is a dummy treatment, sometimes called a sugar pill, although it doesn't have to be a sugar and it doesn't have to be a pill. The placebo effect are things that appear to be dummy treatments, so that the person receiving them believes they're actually receiving a treatment, that they are in fact blind to whether or not they're getting the real treatment or the placebo or the dummy treatment. A double-blind experiment means that not only do the subjects not know which treatment they're receiving, but the people who are measuring their responses don't know it either. Anybody who interacts with them doesn't know. That prevents the bias that the researcher may inject into the experiment. In an experiment, researchers usually hope to see a difference in the responses that's large enough so that we don't think it's just due to luck or chance variation. If that difference is large enough, then we call it statistically significant. We can use the laws of probability, which describe chance behavior, to learn whether the treatment effects are larger than we would expect to see if only luck was operating. If it's more than luck, then we call those differences statistically significant. This is a good definition right here. An observed effect so large that it would rarely occur by chance is called statistically significant. And if I get statistically significant results from a well-designed experiment, then it does imply causation. That is a great indicator of causation. Another type of experiment, instead of a completely randomized design, is what we call a block design. When a population consists of groups that are similar within but different between, a stratified random sample will sometimes give a better estimate than a simple random sample. The same logic applies to experiments. So stratifying is to sampling as blocking is to experimentation. For example, let's say that I've got 10 volunteers and I want to do something about keyboard typing, but I think that people who use smartphones might respond differently than people who don't. So at the outset, when I get my volunteers or my sample, I split them into two groups, those that have a smartphone and those that don't. This is not a random split. I say to them, hey you, do you have a smartphone or not? And they go in the appropriate one. Now, within the smartphone users, I will randomly assign them to keyboard A and keyboard B, and I'll compare their typing speed. With the non-smartphone users, I do the same thing. I'll randomly assign them either to keyboard A and keyboard B, do the experiment, compare the results, and then at the end I can compare the results of my smartphone users with my non-smartphone users to see, in fact, if this difference that I used at the beginning actually mattered. This is called a block design. Again, I'm splitting them up at the very beginning based on some previous characteristic that is not random, but it is relevant to whatever it is I'm doing. So if I think that girls and boys will respond differently to my treatment, I might want to block by gender. A block is a group of experimental units that are known to be similar in some way that's expected to affect the response. They're known to be similar before the experiment's begun. I still need to randomize those. So once I have my blocks, I'll randomize each block and carry out treatments separately within the 2 blocks, or 3 blocks if it turned out that way. A matched pair design is a type of block design where now instead of having a group of people, like a group of smartphone users or non-smartphone users, I actually match people up with very similar other people. So that effectively I have almost 2 clones, and then I will randomly decide who gets treatment 1 and who gets treatment 2 within that pair. That's called a matched pairs design. Sometimes a matched pair is actually you and yourself. So I might choose to do an experiment on you where you're going to be your own matched pair. The trick here is I need to randomize which thing I do to you first. So for example, maybe I want to do something where I measure your arm strength in both your right and left hands. I'm going to let you match with yourself, but I'll randomize which hand I measure first, your right or your left. So I have the randomization occurring within a match, you to you. These are the things, again, that I talked about in this slide, or in this presentation. You can go back and look at anything you may be confused upon, and then we'll look at specific examples to illustrate the points that I've made today.